Alrighty, today we're talking about Chapter 3, Section 5, and as promised, this is going to be a lot of stuff. It's going to be one of those where I don't think you should actually put it on 1.5 speed if you have been doing it. Again, if I watch YouTube videos, I always watch them on 1.5 speed. I can tear through a lot of YouTube videos that way. But this is definitely not one that you should. Right. So the first thing we're going to talk about is we're going to define rational functions. Okay, we've dealt with rational functions before, and so rational functions are quotients of polynomial functions. This means that a rational function can be expressed as, all right, f of x, some function, where p of x is in our numerator is a polynomial, and q of x in our denominator is a rational polynomial. No, sorry. Where p of x is a polynomial and q of x is a polynomial. Right? And of course, q of x not being equal to 0. The domain of a rational function is a set of all real numbers except the x values that make the denominator 0. So for example, the domain of the rational function here below, right? What makes this denominator 0? Well, it's 0 when x is 0, it's 0 when x is 2, and it's 0 when x is negative 5. And of course, we see that down here. Now, real quickly, before we even proceed, let's talk about why the domain is important. Okay, in this lecture, we're going to see the domain being, where the denominator is equal to 0. Okay, but let's switch gears just a little bit and talk about something else with the domain. So let's maybe not make it a super thin one. Here we go. Okay, so let's somehow my straight line tool, I made it crooked. There we go. All right, so this is the first quadrant of a coordinate plane. Now, when I was young, I loved rocket or model rockets, right? Right. What kid doesn't? But anyways, and so I would launch rockets and have a lot of fun with them. And well, I mean, one thing kind of leads to another, and you just kind of theory craft. How can I make this rocket faster, bigger? How can I make it go up higher? And let's just assume I never figured it out, by the way, but let's just assume I did figure it out. Okay, let's assume that young Sherman, he was able to figure out a way to shoot a toy rocket super high into the air and land safely. Huh, man, does my hand shake that much? That's not good. But anyways, um, this is the trajectory of my toy rocket that I shoot. Okay. Now let's just call this function. We don't really you know have the equation for it. Let's just say that the equation's alpha. Okay. Well, let's say that young Sherman emails a NASA engineer, and I'm like, hey, I found out a way to shoot off a mass using nice, clean, cheap, lightweight uh, fuel. Okay, and this is the function of my rocket. Okay, well now let's just say that this particular NASA engineer is not one of the friendliest ones. Um, and all right, let's say for just to really kind of drive this point home, we start here at 0. This is 0, and then let's say it goes up here. Let's say it goes up. I don't know. Let's say it goes up 5,000 feet, right? Almost a mile. Okay, and then it lands over here about 1,000 feet. Okay. And so, looking at this particular function, we know, right, from the things that we know about how functions behave, we know that f of 0 is going to be 0, right? Because right here at 0, does the graph exist? Well, it exists at 0. We also know that f of 100, I'm sorry, f of 1000 is also 0. Okay. Um, Now, I probably should have given more background on this graph, and I'm gonna do it now. Sorry, a little late, but this x-axis is time, right? Or no, is our distance, and the the distance horizontally, and this is our distance vertically. Okay. Now, um, let's say let's just say right now, 500 feet away, 500 feet away. That's when right up here, right? That's when our rocket is at its highest point when it's 500 feet away. So f of 500 is equal to 5,000. Okay. And again, all this makes sense because this is how we have looked at graphs before, and how we have figured them out. Okay. Now let's say that I send this to the NASA engineer and I say that this I've made this rocket, it goes up really high and it doesn't even go out that far, right? Again, clean, renewable, lightweight fuel. Well, let's just say this NASA engineer says, okay, cool, cool. Well, what happens at f of, you know what, 1 million? What happens at f of 1 million? Let's erase this. Mess that up a little bit. Okay, so for some reason I can't get the, oh, there we go. I got the comma going. What happens at f of 1 million? Okay, so 1 million feet away from me. All right, I don't even know how many miles. Let's just see. 1 million feet to miles. All right, it's oh, wow, it's 189 miles. Okay. Anyway, so this NASA engineer says, okay, so what happens at f of 1 million? Well, guys, what happens at f of 1 million? My toy rocket, all right, if it were to continue in this trajectory, at 1 million feet away from me, we are halfway to China, right? Through the ground. And that doesn't make too much sense, does it? So my domain must be restricted on this equation that I send to my NASA engineer. Okay, so what I would say, so I don't have to answer a stupid question like that. Where's my moving tool? Here we go. So what I would say is, okay, so this is my function, but my domain is restricted from 0 to 1,000. Okay, Mr. NASA engineer, you can only use the numbers 0 to 1,000, and then it makes more sense. And that's the whole point of a domain. And I just rambled for like 6 minutes to try and prove that point. But that's the whole point of a domain. The domain is what numbers that you are allowed to use. Okay, so what am I allowed to use in my function? And for these for this class for today's lecture, we're looking just at these values here. What makes the denominator 0? Okay, so we don't have a rocket going off the map. Instead, we're having some number that makes my denominator equal 0. That makes it, because again, the one rule that you remember in math is you cannot divide by 0, right? Well, what the number that makes the denominator equal 0 is not going to be part of the domain. So for this particular example, the domain is going to be every single number that you can possibly think of, except it cannot be 0, 2, or -5. It can be every other number that you can possibly think of in the whole wide universe, except 0, 2, and -5. Okay, so that's the presence of the domain. Hopefully that helps. I don't know. Example 1. So example 1. Oh no, let's yeah, that's not bad. Okay, so let's try that again. So example 1. We are wanting to find the domain of these functions. So if you recall, we had that domain Bible that we had. Hopefully you have it in your notes. And in that domain Bible, I said the domain of a function is always negative infinity to positive infinity, except for 2 circumstances. 1, if we have a variable in the denominator that makes the denominator 0, and 2, if we have a variable in an even index root. Okay, hopefully you have that in your notes. I said, guys, look, do this, put this in your notes. I'm pretty sure put stars by it because it's super duper important. Okay, and this is why. All right, so A, we want to find the domain of each rational function. And again, the domain is what numbers am I allowed to use. Okay, so what I'm going to do is I'm going to just look at the denominator here, and I'm just going to set it equal to 0. I'm going to set it equal to what it can, or set it equal to what it cannot be. And when I set it equal to what it cannot be, then I know what it can be. Okay, so I'm going to set my denominator equal to 0, and this is just pretty easy arithmetic, right? This means that when x is equal to 0, or I'm sorry, when x is equal to 3. Okay, now what I just circled here, what I just circled solves only this equation. That's the only thing. That's the only thing I solved it for. Okay, but again, I solved it for what it cannot be. So the domain of this function is every number but this number that it cannot be. So I would say that x cannot be equal to a positive 3. And that makes sense, right? If we plugged in a positive 3 here, all right, we don't care what the numerator is. The numerator can be anything. It can be positive, negative, it can be 0, it could be a quintillion, it doesn't matter. But the denominator cannot be 0. And when I plug a 3, when x is equal to 3, well, my denominator is equal to 0, and we can't have that. Okay? And of course, we see that. And of course, if I wanted to write this in interval notation, I would say from negative infinity to positive infinity. I don't know why I did that. I'm sorry. From negative infinity to positive 3, union with 3 to infinity. Okay. Or I could write this as, let's move this off to the side so I can have a little bit more room to work with here. Or I could say, I can write, and this is interval notation. If I want to put it in set builder notation, I would say, I would do a little squiggle here, a little curly brace, x such that x cannot be equal to 3. And I like set builder because it's a lot more precise, right? I don't have to write this all this union stuff. Okay, anyways, well, hopefully I haven't been muted. I just actually muted myself there. But anyways, and that is A. Okay. B, again, we're just concerned with the denominator. So we're going to say, okay, so we're going to say x squared minus 9 is equal to 0. We know that, x squared minus 9, that is a difference of squares. And there's a couple ways we can go about doing this, okay? One of them being that we factor x plus 3, x minus 3, because we know that it is a difference of squares. And another way we can do it is we could say, okay, so we can say x squared, and we could add 9 to both sides, and solve that way, okay? And in both cases, we end up with x cannot be equal to a positive and negative 3. All right. So this means that my domain is going to be, if I put it into interval notation, I would say from negative infinity to negative 3, union with negative 3. I'm trying to write this a little small because I got to fit stuff in here. Negative 3 to 3, union with 3 to infinity. And if I put it in set builder notation, a little curly brace, x such that x cannot be equal to a positive and negative 3. Okay, so that's that. Now C, we're going to do on this page as well, right? Because it's pretty darn easy, right? Let's set the denominator equal to 0. Again, we don't care about the numerator. The denominator x squared plus 9 is equal to 0. Okay, well, there is no way that I can plug any number in for x here that will give me a negative 9, right? Again, positive 3 gives me 9, negative 3 gives me 9. There's no number that will give me a negative 9, without using complex numbers, right? So what this means is that the domain is all real numbers, right? Since I cannot turn that into a 0, my domain is all real numbers. Okay, so it took us 15 minutes to get through one example. Today's one of those days. Alrighty, so let's talk about some notation real quick. Okay, so this is some arrow notation. You've probably seen it before, and honestly, even if you haven't, you can probably kind of put two and two together, right? So we have the x, in every one of these cases, we have x pointing towards something, all right? That pointing means that we're approaching. That means x is going towards, all right? X is approaching. Um, if you have some number a, okay, I mean a could be a could be 7, okay, but it's just some number. And if you have a plus sign up there on the exponent, that means we're approaching it from the right side. If you have a minus up there, it means we're approaching it from the left side. And of course, if we have it, approaching infinity and negative infinity, that means that we are, increasing without bounds to infinity or increasing without bounds to negative infinity. Okay. All right. So we had to know that to know the idea of our vertical asymptotes. Okay. Let's put that on the same page here. So a vertical asymptote is a point on the graph that where my graph is increasing or decreasing without bounds because we are not able to touch that particular point. Okay, now it's pretty vague, and I do understand that these letters, that they kind of go in one ear and out the other, or one in eyeball and not out the other eyeball. I don't know, but anyways, so if we have some a here, all right, and we have a graph that looks like this. And of course, we've seen graphs that look like this before, right? That just shoot up like this. And of course, we will see them even more today. But as x approaches a from the left side, right? From the right side, over here on the right side, my function shoots up to infinity. Okay. Over here, as x approaches a, and again, a is just some number on the graph. Okay. I mean, again, it could be 1, it could be 2, it doesn't matter. We're just using the variable a here. As x approaches a from the left side, my function goes all the way up to infinity. Okay, and now on these next two examples, we see that my function shoots down to negative infinity, right? As x approaches a from the right side, we shoot down to negative infinity. As x approaches a from the left side, we shoot down to negative infinity. All right, so that's how that notation works. Okay. And lastly, locating vertical asymptotes. So luckily, locating vertical asymptotes is something that we pretty much just did. All right, so if we have some rational function, that's what that's saying, f of x, where we have a polynomial in the numerator and a polynomial in the denominator, is a rational function in which p of x, or I'm sorry, p of, yeah, it is p of x. I don't know why I said that. P of x and q of x have no common factors, and a is a 0 q of x. The denominator, then x equals a, is a vertical asymptote of the graph. So we just did on the first example, when we found out where the denominator is equal to 0, well, luckily for you, there's not too much more concepts involved here. All we gotta do is just figure out where the denominator is equal to 0. I'm sorry, I got the kind of hiccupy burps. Hopefully it's over. Um, all we have to do is figure out where the denominator is equal to 0, and that's going to be our vertical asymptote. Right? So nothing extraordinary here. Now, um, as far as this lecture is concerned, um, and this might just be a personal thing for me. I'm going to be doing a lot of snipping in today's lecture because I want to show you the graph. Okay. Now, of course, we're halfway through this semester, and you know that I don't take the lazy way around. I explain everything. I do the computation and everything that's needed to be done. Okay. But today I'm going to be doing quite a bit of snipping because I want to show you the graph and show you how things behave as opposed to showing you how things are algebraically. So I don't know. Hopefully that's okay with you guys. Okay. So. And of course, when necessary, I'll do it if I need to. All right, so let's put this here as well. There we go. Alrighty. Um, so example 2 reads, find the vertical asymptotes, if any, of the graph of each rational function. Okay, so starting with the first one, A. What we're going to do is we're going to take this denominator and set it equal to 0. Okay, now by setting it equal to 0, similar to, well, that's pretty nice. That's exactly what we did at B. Well, the denominator being the exact same in B, x squared minus 9. Oh, it's the exact problem oh, perfect. Okay, I didn't realize that. I'm sorry. All right, so it's the exact problem that we essentially saw. So on example 1, I did the difference. I showed that it was difference of squares, and I did the add 9 to both sides and take square root. Okay, in both cases, we saw that we had x could not be equal to a positive 3, and x cannot be equal to a negative 3. And what does that look like graphically? Well, we have a vertical asymptote right here at negative 3 and at positive 3. Okay, see how that works? So right here at positive 3 and negative 3, I was unable to, or the graph is unable to essentially cross over that line there. Okay, because that is where the graph, it's not part of the domain. It does not exist there. Okay, and actually, I am glad I snipped that, because obviously I want to show you how that works, how that behaves. All right, now B is a little bit different. Notice how B has the exact same denominator, okay? But we're not going to have a vertical asymptote at at positive 3 and negative 3. Of course, you can see that down here in the graph. And why is that? Well, let's explain it. And so this is where I, make the big bucks, where I explain things to you. Okay, so B was x plus 3, and it's over x squared minus 9. Okay, so what we must do for these kind of problems is we need to factor the denominator. Okay, every time factoring the denominator is always the most important, right? And of course it factors into x plus 3, x minus 3. At this point, what you're going to do is you're going to say, okay, so the domain the domain of this function is going to be all real numbers except, well, let's put an arrow. The domain is that x cannot be equal to a positive and negative 3. I can use every single number. Sorry, I can use every single number except for a positive and negative 3. Okay, but now when it comes to graphing it, it's a little different. All right, so what we're going to do is we're going to look at this particular function and we say, okay, well, the x plus 3's cancel, and so this means that my function is now going to be 1 over x minus 3. Okay, and that is the graph that we're going to be using there. All right, so notice the graph here. This is the one we just did. Notice here at positive 3, our graph does indeed not exist. All right, but at negative 3, it looks like we're kind of going through negative 3, doesn't it? Okay, but there's a hole in the graph there. Okay, and if you graph this on your calculator or Desmos or something, and you try to go over negative 3, it'll say undefined. Okay, so we're still following the rules here. It's just we don't happen to have a vertical asymptote. Okay, now C well, C in example 1, I said that there's no way we can make that denominator equal to 0, and so it's just a normal graph, right? There's no vertical asymptote and there's no holes. So hopefully you see the relationship between the domain that we discuss and the idea of vertical asymptotes and holes in the graph. Alrighty, next up we're going to talk about horizontal asymptotes. All right, so if we have a vertical asymptote, then certainly we have a horizontal asymptote, right? So the horizontal asymptote. All right. The definition of a horizontal asymptote: the line y equals b is a horizontal asymptote of the graph of a function f if f of x approaches b as x increases or decreases without bound. Okay, so now unlike the vertical asymptote, a horizontal asymptote can and most or a lot of times will go over the horizontal asymptote. It's just that the horizontal asymptote is basically kind of like the behavior of a graph. So let's examine something real quick. Okay, so let's just let's just have us let's make us rather a scatter plot. Okay. All right. So notice how in this scatter plot, I mean, we can obviously tell that there's a behavior of this graph, right? The behavior is that this graph is just kind of shooting up, right? I mean, it's not exact, but it's kind of shooting up. And that's how horizontal asymptotes behave, right? Especially looking at this example here. We obviously cross over that dotted line, but we see that as we approach infinity on this side, we get closer and closer to that horizontal asymptote. And of course, on these two examples, it behaves like you would think with a vertical asymptote. But horizontal asymptotes aren't, there is no hard and fast rule where there are holes in the graph. It's just basically the behavior of a function horizontally. Okay, so locating the horizontal asymptote. So locating the horizontal asymptote is it's pretty easy. It is pretty easy. Okay, um, and here's why. So again, the first part of this definition is basically just mathematical jargon. This is again things that you don't necessarily have to be concerned with as unless you're going into a pure mathematical course. Right? Pure mathematical course being proofwriting, but it is necessary. Something that we need to pay attention to, though, because these definitions are very precise, is the degree of the numerator and the degree of the denominator. Notice that the degree of the numerator is n, and the degree of the denominator is m. Okay, so here are the three rules that we're going to look at to determine the horizontal asymptote. They're super easy. Slanted asymptote is a little bit tougher, but horizontal is super easy. So what are the rules? Well, if n is less than m, so if the degree of the numerator is less than the degree of the denominator, uh, then the horizontal asymptote is just simply the x-axis, or y is equal to 0. If n is equal to m, so if the degree of the numerator is the same as the degree of the denominator, then the line a of n over b of m, right? A sub n over b sub m. Notice that is just the leading coefficients. That's just leading coefficients. That will be the horizontal asymptote of the graph. Okay, and of course we'll see examples of this. And if n is greater than m, right? So if my numerator has a degree greater than the degree of my denominator, then the graph has no horizontal asymptote. Okay, so let's examine that, and I'll put this on the same page. Um, let's see, we'll do this, put this over here, and I'll try and put the graph in here. 1 second. So this is A. Probably could just snip all of them. That's fine. That's A. This is B. And 4 is greater than, and we have C is nothing. Okay, so A, B, I don't like it that big and thick. I like to be consistent. There we go. A, B, and then C. Notice there's nothing for C. Alrighty, so all we're going to do is look at the very first term of each polynomial. Okay, so looking at A, is the degree of the numerator greater than the degree of the denominator? Well, the degree of the numerator is 1, right? 4x to the first power, and the degree of the denominator is 2, 2x squared. Okay, so the degree of the numerator is less than the degree of the denominator, right? So did I miss something? No. Okay, it actually doesn't. It actually doesn't show. Is that it? Ah, there it is up there. All right, so I had that little mess up. Sorry. Let's fix this. There we go. Okay. Sorry about that. I didn't realize it. Okay. So the degree of the numerator is less than the degree of the denominator. So we're looking at the first rule here. If the degree of the numerator n is less than the degree of the denominator m, then my horizontal asymptote is the x-axis, or y is equal to 0. And we see that here. Okay, we see that, and of course, as you can tell, the graph shoots right through 0. But of course, as we go to infinity, we get very, very close to 0 without actually getting there. Okay, we just see the behavior of the graph. All right, so that is an example of a horizontal asymptote at 0. Now B, notice how the degree of the numerator is 2 and the degree of the denominator is also 2. So therefore, the horizontal asymptote is going to be the ratio of the leading coefficient. So the leading coefficient here is 4 divided by 2. 4 divided by 2 is 2, and we have the horizontal asymptote up here at 2. Okay, and again, that's just following along with rule number 2 here. And rule number 3, if the degree of the numerator is greater than the degree of the denominator, then we have no horizontal asymptote. We have what's called a slant asymptote, which we'll talk about. I don't know if we'll talk about that today, but it's there. All right, notice how the degree of the numerator is 3, the degree of the denominator is 2. 3 is greater than 2, and therefore we have no horizontal asymptote. Okay, so that's that behavior. All right. So we've talked about transformations of functions. We talked about our parent functions. Well, now we're going to have a new parent function, right? The 1 over x squared. I'm pretty sure that is part of, that was at least part of my parent functions that I went over. But in case it wasn't, then it is now a new parent function. But now we know the behavior of these parent functions, and so we can solve these accordingly. Okay, so we know that the graph 1 over x squared looks like this, right? We have that vertical asymptote at 0 because if you plug in 0 right here for x, we have a vertical asymptote. And of course, you know, the degree of my numerator is less than the degree of my denominator, so we have a horizontal asymptote here. All right, well, if we were to subtract 2 from the function, subtract 2 from the variable, we know that if we add or subtract from the variable, we make it a horizontal shift. So we have the horizontal shift to the right 2 units, and then we know that the last transformation you do every single time is a vertical shift, is a +1, so we go up 1. Right, and well, that's it. Right, again, it's hard for me to shake the, feeling lazy doing this, but I feel like it's better if I snip these than if I draw them. All right, so graphing rational functions. So the strategy for graphing a rational function. All right, there are a lot of these. There are a lot of these things that we must do to graph a rational function. Okay, and again, I'm not necessarily on board with the straight up 1 through 7 algorithm because as you progress through your math course along with all of your courses, you're not really thinking about these algorithms, right? So I want you to be able to kind of know what to do without doing the 1 through 7. Now if the 1 through 7 helps you, it's the way it is. It's fine. And we'll cover these one by one. All right. So the following strategy can be used to graph a polynomial rational function where p and q are polynomial functions with no common factors. So determine whether the graph of f has symmetry. Okay, so what we can do is we will substitute in negative x for x and figure out if we have symmetry. Okay. Number 2, we're going to find the the y-intercept. Of course, we find the y-intercept by setting x equal to 0. Step 3, find the x-intercept. Of course, we find the x-intercept by setting y equal to 0. We're going to find any vertical asymptotes by solving the equation the denominator equal to 0. All right, again, just set the denominator equal to 0. We're going to find a horizontal asymptote like we did before. We're going to plot at least one point between and beyond each x-intercept and vertical asymptote. And then we're going to use all the information that we have obtained to graph the function between and beyond the vertical asymptotes. So again, that's a lot of stuff, right? But let's just attack this the best that we can. So step one here was to find any sort of symmetry. Okay, so I'm gonna put step one. That's going to correspond with the steps that we saw on the previous page here. Okay, so step one, we're going to determine any sort of symmetry. Okay, so what we're going to do is we're going to say, okay, so f of negative x. Okay, so my pen is not behaving correctly right now. So f of negative x. Okay, so f of negative x, we're going to substitute in negative x everywhere where we see x. Okay, so 2 times negative x is a negative 2x minus 1 over negative x minus 1. Okay, so we have to ask ourselves, all right, so is this function the exact same as this? Well, no, because one of them has a negative 2x, one has a negative, and negative x, and one of them, they're positive. Okay, well, is my function my function in blue, is it the exact negative of my original function? Well, no, because if it was, that would be a plus 1 and that would be a plus 1, right? It's not the exact negative. So it's not the same, nor is it the exact negative. So this particular function does not have any sort of symmetry. Okay, so no symmetry. Let's put no symmetry. We're just going to put sim. Okay, so that's step one. Step two, we need to find the y-intercepts. Okay, so by finding the y-intercepts, we need to set x equal to 0. Okay, so the y-intercept, we set x equal to 0. So we're going to have 2 times 0 minus 1 all over 0 minus 1. So we end up with negative 1 over negative 1, or in other words, 1. Okay, so we have a y-intercept at 0, 1. Okay, and of course we are only going to have one y-intercept because these are functions, and obviously functions must pass that vertical line test, and so we only have one y-intercept. All right, so step three, a little bit, I wouldn't say tougher, but not nearly as easy, is find the x-intercept. Okay, so the x-intercept, what you do is you set y equal to 0, so you're going to have 0 is equal to 2x minus 1 over x minus 1. Okay, well, if we multiply both sides by x minus 1, we end up with 0 is equal to 2x minus 1. And in other words, we have, if we solve for x, we have x equals 1/2. So my only x-intercept is 1/2, 0. Okay. And again, that's just in case I lost you. I just take this, solve for 0, I add 1 to both sides, I end up with 1 is equal to 2x, and then divide both sides by 2. Probably. So step 4, we need to find vertical asymptotes. Okay, so vertical asymptote, we'll put VA, my vertical asymptote. Okay, what I'm going to do is I'm going to set my denominator equal to 0, and I'm going to figure out what I cannot use. Keep that in mind, what I cannot use. Okay, so I've got x minus 1 is equal to 0. This means that at x equals 1 is my vertical asymptote. Okay. Next up, we're going to find my, let's snip this, get to my horizontal asymptote. Pretty sure horizontal asymptote is next. If it's not, oh well. No, not oh well. Let's go back. Let's make sure. Let's make absolutely sure. I mean, after vertical, yeah, after vertical is horizontal. I figured so. I didn't want to actually oh well that, sorry. Okay. All right, so we have the vertical asymptote at x equals 1. Let's go back. Yeah, at x equals 1. All right, and step 5 is a horizontal asymptote. All right, so looking at the degree of my numerator and the degree of my denominator, we see that the degree of my numerator is 1. The degree of my denominator is also 1. So my horizontal asymptote is going to be the ratio of my leading coefficients. Okay, so it's a 2 in front of the x in the numerator and a 1 in front of the x in the denominator. So that means my horizontal asymptote, my right, h, my horizontal asymptote is going to be at y is equal to 2. Okay. Um, Next up, I mean, step 6 is plotting points. But let's just jump to step 7 just for right now, okay? All right, so excuse me. Let's draw the graph here. I'm probably just gonna snip the points, but I just want to jump straight to the graph real fast. Okay, so first of all, we had no symmetry, no big deal. We had a y-intercept at 0, 1, right here. So we had a y-intercept at 0, 1, so about right. So what am I doing? Oh, gotta change it to pin mode. Right here, about 0, 1, we had a vertical asymptote. I'm sorry, my y-intercept. My x-intercept is at 1/2 and 0. Okay, so about right 1/2, maybe ish there-ish, right? Because if this is at 1 tick, 1, 2, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. Okay, so we're trying real hard here. Um, that's my x-intercept. My vertical asymptote is at -1 and +1. Okay, so -1 and +1 is going to be my vertical asymptote. So uh, how would I draw that? Well, what we're going to do is we're just going to put basically we're just going to put some horizontal lines. A horizontal line through here and there. Okay, so this is my vertical asymptote. Wait a minute, did I say +1, -1? Oh, it's just that +1. Okay, so sorry about that. Let's erase that. Go ahead of myself. It's just a mistake. There we go. Okay, so sorry about that. I just misread that. My vertical asymptote is at just simply at x equals 1. Okay, so I draw a dotted line there at x equals 1. I have a horizontal asymptote at x equals 2, or I'm sorry, y equals 2. So I have a horizontal asymptote right here. Okay, now the way this graph behaves, I know that we have a vertical asymptote at let's see, at this line right here. Okay, now step 6 was to essentially plot points. Just to get a rough idea of where what should go where. Okay, and I'm gonna go ahead and snip this and put this at 6, so we have an idea of where they go. Okay, so at x equals -2, there we go. Sorry about that. Where x equals -2, f of x is 5/3. When x equals to -1, y is equal to 3/2, and we can see that so on and so forth, right? And by plotting those points, and let's just plot it. So at -2, 1, 2, x equal to 5 1/3. So it should be somewhere around 5 1/3, but somewhere about here. Well, let's put the pin back on. Somewhere about here. At -1, it's 3/2, so it's -1, it's 1 1/2, so it's about right here. At +3/4, it's at -2, so about right here. At +2, it is 3, so +2, so it's way up here. And at 4, it is 5/7, and that's off the screen, okay? But anyways, so the way this graph behaves, and I mean 4 would be right here, I guess, is we basically just connect these dots, right, like this, and then of course we know that this, we know there's a vertical asymptote right here, so we're shooting off to infinity. But this is a rough sketch of what this graph looks like. And as usual, I'm going to give you the better graph, so you have a better idea, better understanding of one moment. Okay, I'm really sorry. I don't know. I don't know. I got the sneeze, the hiccups, the burps. Today's a bad day, I guess. But anyways, this is how we take and look at graphs on this is how we graph functions just with the information that we're able to find. Okay. If you were before this lecture, if I said graph this, you would have no idea how to graph that, or at least I don't think most of you would probably would not have much of an idea of how to graph that. Okay. Next up, we're going to talk about slant asymptotes. Um, is it asymptote or asymptote? I don't know. Um, however you say it. I guess asymptote is a lot less, um, I don't know, bad wordy instead of asymptote. Sorry, don't tell anybody else. We're having this conversation, please. Uh, Alrighty, so the slant asymptote. Okay, so uh, let us we see a graph here, and we can kind of how I told you like with a scatter plot, you can kind of like you can kind of map out exactly where something exists. Well, same thing with the slant asymptote. Ugh, shoot, asymptote. All right, so to examine the graph, right, we have x squared plus 1 over x minus 1. Notice how the degree of the numerator is larger than the degree of the denominator. And way back here, well, no, not there, way further back than that. Back here, we said that if the degree of the numerator is greater than the degree of the denominator, then we have no horizontal asymptote. Well, we have no horizontal asymptote, but we do have a slanted one. Okay, and of course, that's what that means right here. We have a slanted asymptote. Okay. So the graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So it must be, and it can only be, 1 more. Okay, and if that's the case, the equation of the slant asymptote can be found by division. For example, to find the slant asymptote for the graph x squared plus 1, x minus 1, we divide x minus 1 into x squared plus 1. Since this is a first degree polynomial, we are able to do um, we're able to do synthetic division, and pretty sure, can't remember. I mean, yeah, we had to have covered synthetic division, right? Um, I don't remember if we did in this class or not. I don't know. But anyways, synthetic division. I'll give you a good reminder of it. But with the synthetic division, we end up with the equation 1x plus 1 plus 2 over x minus 1. So this is the equation of my plus remainder over divisor. This is the equation of my slant asymptote. Okay. And then coming down here, observe that we have the equation of the slant asymptote is y is equal to x plus 1, and then that's that plus the remainder over divisor. We'll talk about that here in a moment. Oh, there it is, remainder over divisor. Okay, so it's probably best if, I mean, I could read this, but I think it's best if, for time's sake, because I know we're at 48 minutes, and I know that not just your minds, but my mind as well, can only take so much of anything. So let's just jump straight into an example. I try to keep my lectures at about 45 minutes because I mean that's still 35 more minutes than what the average person is willing to use. Okay, so I think yeah. So this is the last example, so that's good. All right, so find the slant asymptote. So we have my numerator is exactly one more than the degree of my denominator. Okay, so if it's exactly one more than the degree of my denominator, then I'm able to do division to figure out what my slant asymptote is. So whenever you set up synthetic division, right, your divisor up here is going to be the opposite sign of this denominator here. All right, it's x minus 3, so my number is going to be a positive 3. Okay, and then the way we set up our synthetic division again here is we're going to look at my numerator, and we're only going to put the leading coefficients, and we're going to put them in descending order. Okay, so we have an x squared minus 4x minus 5. Now, in this particular case, all the x's are accounted for. Okay, so whenever you have a second degree polynomial, you have an x squared, plus x plus some constant. On the previous page, we had x squared plus 1. We skipped the x, didn't we? We skipped right over the x, but whenever you do synthetic division, you have to account for that term. It's essentially a 0x. Okay, so it's not necessarily explained too well here, but you need to account for every single term. And again, for this particular problem, every term is accounted for. There's a number in front of the x squared, there's a number in front of the x, and there's a constant. On the example given here, there is no number in front of the x because there's no x that exists, but we account for it by saying 0x, right? This is x squared, we have 0x, and then we have the plus 1. Hopefully that makes sense. All right, so by accounting for that, I've got a 1 for the x squared, a negative 4 for the x, and then a negative 5 for my constant. Okay, so whenever we do that, we just put a little equal sign here and then put a little box down here because that's the remainder. So if you haven't done synthetic division in a while, pay close attention. This is exactly how synthetic division is done, and I'll do long division as well, just to make this lecture extra long. What you do is you bring down the first number, so 1. You take this number and you multiply it by this number. 1 times 3 is 3. Then you do the arithmetic here. Negative 4 and a positive 3 gives you a negative 1. And then you take this, negative 1, multiply it by 3. So you get a negative 3. And then you do the arithmetic here. Negative 5 and a negative 3 is a negative 8. And we're done. Okay. And on the previous page, we saw that the way you write your solution is you write your equation, and then it's plus the remainder over the divisor. Okay, so what does that mean? Okay, so here's how this works. In synthetic division, you can only 100% of the time, you can only use synthetic division when your divisor is a first degree polynomial. That's the only time you can ever use synthetic division. Okay, and of course I'll also show you the long division way, but this is the only time you can use synthetic division. And when you do that, this equation down here now becomes, okay, so we have a 1, a negative 1, and a negative 8. Okay, so what does that even mean? Well, what you're going to do is you're going to look at the degree of my numerator. Okay. Well, this particular numerator is a second degree polynomial. If I'm dividing it by a first degree polynomial, which by the way, again, synthetic division, you're always dividing by a first degree polynomial. Then you're gonna take the numerator's degree and just take it down 1, right? If this was a 17th degree polynomial, and I did synthetic division, again, synthetic division has to be only a first degree polynomial, then I'm going to take it down 1 from the 17th power down to the 16th power. So this is going to be, this 1's going to come down. It's going to be, we're going from 2, we're going to go down to 1. It's going to be x, and it's going to be minus 1. And that's going to be plus the remainder, which is in this box here. So plus negative 8 over my divisor, which is right here, x minus 3, because I'm dividing by x minus 3. That's what's up here, x minus 3. Okay, and this is the equation of my slant asymptote. Okay, now let's do long division, because you will have some long division problems here. Long division is a lot more tedious than synthetic division, and I know that sucks. Okay. So the way long division works is you're going to set this up like you did long division way back in 3rd grade. And I know you probably don't remember it, because I know I didn't remember it when I started doing this, right? I mean, once you did it and figured it out, that's fine. And then calculators were introduced to you, and you're like, I don't even know long division. Anyways, whatever. All right. So the way long division works is you're just going to look at the first term right now. Okay? So you're going to say x squared divided by x. Well, x squared divided by x is just simply x. Okay, so what we're going to do is we're going to put that x. Oh, oh shoot. Now let's go back. I usually underline them. I don't square them like that. So x squared and x. So you're going to say x squared over x is equal to x, and you're going to put this x over this x here. All right, makes things nice, neat, and orderly. The next thing you're going to do is you're going to take this x and you're going to multiply it by these two. Okay, so x times x is x squared. X times a negative 3 is a negative 3x. Now, here's where here's just some uh, notation that you need to do every single time. Right? Every single time you do this, you're going to put the equal sign down here, and as soon as you're done with the equal sign, change the sign of everything above it. Okay? So that negative x squared, I'm sorry, that positive x squared is going to turn to a negative x squared. That negative 3 is going to turn to a positive 3. As soon as you put this equal sign there, immediately change the sign of all the numbers above it. If you do that every single time, then you won't make mistakes. Okay. Anyways, then we're gonna do the arithmetic. Okay. Well, x squared minus x squared, that's 0. Negative 4x plus 3x is going to be a negative x, and then we have a negative 5. Okay. And then we do the exact same thing again. So we're going to say, okay, so we're going to say negative x divided by x. Okay. Well, negative x divided by x, well, that's just going to be negative 1. So that's a constant there, so you're going to put it over the constant. And then you're going to do the exact same thing. You're going to multiply the divisor by that number there, right? So let's go ahead and do that. We have a negative 1 times x, so that's going to be a negative x. Negative 1 times a negative 3 is going to be a positive 3. Okay. Oh yeah, okay, good. And then as soon as I put this equal sign here, I change the sign of everything above it. So that negative x turns to a positive x, and that positive 3 turns into a negative 3. And then we do the arithmetic, right? Negative x and a positive x, well, that's just nothing, right? Let's just go and mark them out like that. And then negative 5 and a negative 3 gives you a negative 8. Okay, and then you essentially stop there. But let me tell you why you stop there. If we were to continue with the long division process, we would say negative 8 divided by x. Well, negative 8 divided by x, well, that's just negative 8 divided by x, right? So that's why we stop there. So this negative 8 is just going to be my remainder. That's just going to be my remainder. Okay. So if you recall, the solution is written in your quotient. So you're going to say x minus 1. Sorry. X minus 1 plus my remainder, which is negative 8, plus my remainder over my divisor, which is x minus 3. Okay, and let's look on the previous page. It's the exact same thing. Okay, so obviously long division is a lot more tedious, but long division works with every single polynomial. Synthetic division only works when the denominator is a first degree polynomial. Anyways, again, as promised, today was going to be a long day. Sorry we went an hour, but I mean that's just part of it. Good luck. Email me if you have any problems.